Okay, it's already on the webinar side, so recording is on. So Daniel, you can start whenever you're ready. Welcome, everyone.
Thank you. Then we can start with the webinar. So welcome, everyone, to our webinar on executing and debugging multiple GPU codes on Alps. I am Daniel Ganellari, and today with me I'm joined by Andreas Fink, Mikael Simberg, Jean-Guillaume, and Ioannis Makanaris. This is the team that will support you with the questions in the online document throughout this session. So I'm going to continue with. So in the first part, I'll focus on the new GH200 architecture, NUMA characteristics, SLURM, best practices, and performance benchmarks. While Jean-Guillaume will continue with the second part of the talk with NVIDIA tools, Linaro and Score or Scalasca, if the time allows for that. Yeah. Here is the link, which you probably have received also today by email, where you can ask your questions. So please do so during the talk. So then our team can answer them as we speak. Also, you can ask questions after the webinar, so that we'll try to answer them as well. If you want to listen to this online afterwards, so just put the question there and we'll try to answer it. Okay, so having said that, we can start with a hardware overview of Grace Hopper GH200. Sorry. Okay, so the Alps system features the Grace Hopper GH200 architecture, and each node contains 4 GH200 superchips, which has one Grace CPU and one Hopper GPU. And together they connect through this chip-to-chip NVLink. So each of the modules connects through an NVLink connection, which is 150 gigabytes per second per direction. We have 4 network cards, which connect to the slingshot switches, each with 25 gigabytes per second, which gives us a total node-to-network bandwidth of 100 gigabytes per second. So if we look at a single module, we see here a combination of 72-core ARM Grace CPU with an H1 GPU. The CPU has 128 gigabytes of host memory, which is 2x more compared to what we had on old Piz Daint, and the GPU has 96 gigabytes of memory, and that's 6x compared to what we had before. What makes this architecture, I would say, new or revolutionary, if I may say so, is the 900 gigabytes per second chip-to-chip connection between the CPU and the GPU, which is approximately 56 times faster than on old Daint. So this extremely fast NVLink enables a fundamentally different memory architecture on Alps. If you want to know more about the architecture of this, data paths, there is a case study paper from ETH Zurich from the group of Professor Torsten, together with in collaboration with CSS. So here you have the link to that paper. So I think, yeah, to recommend that. So let's move on. So all these 4 modules that you saw, so all these 4 modules together create a single node with 288 CPU cores. So all memory forms unified address space. So both CPU and GPU memory are accessible from either processor now. So if we go into a Daint node and you check for the total available memory, you will see that the system will report 896 gigabytes of memory. Something also that you need to know is that CPU and GPU memory from different modules are organized into different NUMA domains, which we'll see a little bit more in detail later on. But for now, let's see how does this new architecture affects developers from the developing point of view. So this table highlights a key difference, let's say, when migrating application from Piz Daint to GH200. So on Piz Daint, adding GPU support required significant code changes to manage GPU memory and to write GPU kernels. But on the other hand, with GH200, the unified address space that it has, and also this new fast chip-to-chip interconnect, they offer major benefits for CPU to GPU applications. So applications that also need it, but also will need frequently to move data between CPU and GPU can now do so with, let's say, drastically reduced overhead. Yeah. Let's jumping on the NUMA domains. So understanding NUMA domains is critical for GH200 performance. So NUMA stands for non-uniform memory access, and it actually means like memory access time depends on location relative to the processor that you are working with. So you should be familiar with our old Piz Daint MC partition. So we had a system with 2 CPU sockets, and accessing memory of other socket is lower. So, but what is the impact on developing code, multi-threaded code, high-performance code, if you are going to have to do with NUMA domains? So there are these 2 possibilities. You either write NUMA-aware code, like observing first touch policy, and other things which we'll look at later, or the simplest way is to launch at least 1 MPI ring for each NUMA node. So GH200 extends this, extends this NUMA concept to include GPUs as well. So each node now has 8 active domains, 4 CPU modules, and 4 0, 1, 2, and 3, and then 4 GPU modules, with the difference that the GPU modules are now not continuous anymore. And you see there are 1 that is used for the H100, 1 GPU that we have on Alps, and then you have there are still 7 non-used nodes, and that's for the multi-instance GPU, which basically means that it's possible to also configure and add to have a system with more Hopper GPUs as well, or you can kind of, it's still a hardware configuration, but you can actually split this GPU into, let's say, isolated multi-instances GPU that you can later use. Okay, so to see this information, you can just use the NUMA control -H for hardware on any node on Daint or on Alps. This will report 36 nodes for you. So there are 4 CPU nodes, NUMA nodes that we reported, each with 72 cores and 128 gigabytes of RAM. And then the GPU modules 4, 12, 20, and 28, each with 96 gigabytes of RAM. So if you see here, I added node 4, which is the GPU of module 0. You don't see any CPUs here, but you only see the memory for the GPU. While for node 5, don't see anything because that's the empty node of module 0. It's here, this one here. Okay, so only 8 of 36 NUMA domains are used, and remaining domains are reserved for MIG technology. So there is also more information that this command offers, which basically gives you the physical distances between NUMA domains. So we have NUMA distance value 40. That means that you have a CPU to CPU connection on different modules. For example, 1 with 0, so you have CPU to CPU, but that's different modules. You have 80, which is CPU to GPU on the same module. 4 and 0, they are on the same module, but one is the CPU and the other is the GPU. We have a distance of 120, CPU to GPU on different modules, right? So, for example, 12 to 0, okay? And then we have 255 GPU to GPU on different modules. So, yes, GH200 is the first system at CSCS where GPUs appear as NUMA nodes. So what's important to remember, because it's when you develop your code or when you work with GH200, is now that memory allocated with host APIs can be accessed by all CPUs and GPUs in the compute node. Physical memory placement is decided by first touch principle, which means that if you're allocating memory, but then writing with a CPU, only CPU threads, then this memory will be allocated on the host memory. Otherwise, if you do some kind of CUDA memset or something, we'll see some examples later on, then it will be allocated on the GPU memory. Now, automatic page migration, which is a repeated access to memory on a different NUMA node, can cause memory to be migrated. For example, if you have some memory residing on the host memory, and then this is really frequently accessed by the GPU on a different NUMA node, then most probably this will continue to be accessed frequently. So it's better to move this memory closer to the GPU, to the GPU or to the NUMA node, and that's what automatic page migration does, right? The thing is that most probably you received the information yesterday that this feature is now disabled on Daint and Clarendon, and that's done because to address performance issues for nickel-based workloads, like, for example, LLM training. It's also important to note that memory allocated with CUDA malloc now cannot be accessed from CPU and by other GPUs on the compute node. And even if automatic page migration was working or was enabled, sorry, then page migration on this type of allocated memory would still not work. So you had to do that manually yourself. Okay, I think I'm done with this slide. So here are some examples on how to show that we can pass system memory to GPU kernels. Here is the simple CUDA kernel, which adds 2 arrays into a third one. However, the allocation here is done by the STD vector, right? Which uses new to allocate memory, system memory. However, the initialization of the elements is done by the constructor of STD vector. This is done with a single CPU thread, which means that the memory in this example will be placed in the host memory. Okay, so you can still pass this memory to the GPU kernel, but this memory will be on the CPU. Another example is when we have the same kernel, same GPU kernel here, but instead of using the STD vector, now we are using some arrays, but we don't want to use STD vector because we don't want the allocation to happen on the CPU, so that we just allocate the memory, but then the first touch happens on the GPU using CUDA memset. So the memory in this case will be placed on H100 HBM3 memory of the GPU, and then you can still, the same way, pass this memory to the kernel. So yeah, as a summary, So GPU memory allocated with CUDA malloc behave the same as on previous machines. So the CPU and other GPUs can't access it. Also, no automatic page migration. System memory is now also accessible by GPUs. NUMA memory placement decided by first touch policy. It's a little bit tricky to get right. And it's very important that if you're designing code to run with 1 rank per module, we'll see some examples later on, it's still a reasonable choice in most cases, because so in comparison to writing NUMA-aware code, right, you can still take advantage of unified memory and no need to manage multiple GPUs per process yourself in your code or deal with NUMA effects. Okay, so now we jump to SLURM practices. So let's talk about running jobs effectively on GH200. As we saw before, each module has 72 cores and 1 GPU. And SLURM distributes MPI ranks across modules by default. This means that each MPI rank within a node will be placed on a different module. This is important to know. And this is the case that I talked about, like 4 MPI ranks per node with 72 cores. So this is the most natural way to say, let's say, to run on GH200. So 4 ranks per node, 1 per module, which gives you each rank 72 cores, 1 GPU, and avoiding NUMA effects in this way. Something you need to take care is that, of course, SLURM will do the mapping for you, but what SLURM will not do is set the CUDA visible devices, right? So if you haven't set the CUDA visible devices or specified GPU per task in this case, then due to CUDA active device or default active device, which means that all this work will be, say oversubscribed to GPU 0. And then because our nodes are configured in such a way that it will still allow the oversubscription, you won't actually get a failed job, but you'll see, let's say, degrading performance. Okay, so this is like the thing to look for if you are doing something. So you will not get a job failure, just the performance. You'll see difference. So make sure either to set this one or export CUDA visible devices. Something else that changed on Daint is that now enabling CUDA aware MPI is default on Daint Alps, so you don't have to set that up. But on the other side, this is a breaking change for non-GPU aware MPI code, right? Because they are not linked or they have not enabled the CUDA aware MPI on their code. So if you try to run that, it will fail with GTL library, which is responsible for CUDA aware MPI is not linked in your application. So to fix that, you can just either export this and set it to 0, and then your code will run just fine. But what I would recommend is that you actually add GPU aware support, GPU CUDA aware MPI support to your code, because then it's a lot of performance that you gain by that. So for interactive sessions, when you want, for example, to develop or debug your code, and you need more control over the SLURM affinity, we've created this affinity script, that it says the CUDA visible device based on local rank, and uses the NUMA control to bind each rank to the correct CPU and memory domain. Okay, so basically the CUDA visible devices are 0, 1, 2, and 3. So this does not match with the NUMA numbering of the GPUs. That's why you need to do a mapping here. And this maps the NUMA node like based on the local rank. So local rank 0, NUMA 0, and so on. Basically very similar to what SLURM is doing on the inside. This is like a printing script for debug, which tells you basically which rank is which GPU and what NUMA node. And then you can bind the NUMA resources like the CPU and memory bind to the NUMA node that this rank is going to run on. To use this script, the difference here is that you can run as normal, like again, but one node and 4 MPI ranks. Then you call this affinity script before calling your executable. Okay, then what else? So what if let's say your application needs more than 4 ranks per node, right? So on Piz Daint, you could use the Cray CUDA MPS environment variable for GPU sharing, but on the GH200, this needs to be called manually using this MPS wrapper script that we provide in the knowledge base under user guides running jobs. You can find that there. So what does MPS do is basically it coordinates GPUs across GPU access across multiple processes, right? Improving in this way the performance when ranks share GPUs. So without MPS, your application would still be allowed to run, but you would see performance degrading. So what do I mean? Again, in the same situation, if you omit the script, your code will not fail, your job will not fail. It will still run, but you'll see degrading because of how we have configured our node. They are in compute mode, and it means that it just allows oversubscription. So your job will not fail, it will still run. So in summary, use 4 ranks per node for natural mapping when you can say saturate your GPU with 1 rank. If not, and you have smaller jobs per rank, which are probably not enough to saturate the GPU on their own, or for example, for legacy code, where they have a very fine domain decomposition, say you have 1 domain assigned to each core, then that's the case when you can use MPS. And if you still want to do 1 rank for the full node, then you have to write NUMA aware code and manage multiple GPUs in your code as well. There are a lot of examples, submission scripts, wrapper scripts in the supported applications from CSCS. You can find it here on the knowledge base on how to best run different applications on GH200, so with the proper scripts, wrapper scripts. Okay, so then the last part of my part. So now we're going to see the performance that we can expect from GH200, right? So running benchmarks on a system is, let's say, valuable not just for understanding hardware capabilities, but also for validating your software environment, compiler flags, environment variables, SLURM setting, and API usage. So what we test here, we start by measuring compute flops for the performance, and we use a matrix multiplication on CPUs and GPUs. We have this benchmarking tool called NodeBurn. You can check that and also run that on Alps and see if you get the same results. So what we are doing here, we are doing a GPU gem, so matrix multiplication of this size, and we are running on one node with 4 MPI rings, as we explained before. So again, if you have not exported your CUDA visible devices, then make sure to use the Affinity, the interactive Affinity script. Otherwise you'll not get this performance, which is peak GPU performance, the best you can get. We really get very good performance doing this on the GPUs. For each GPUs. Now, if we switch now from double precision to floats and use the Tensor cores and enable them also in cuBLAS using, for the data we use float point, but we use TF32 where the cuBLAS Tensor operation math are enabled in this way. So if you want to use this with cuBLAS, you should set the math mode to this. And if you want to use our tool, NodeBurn, then make sure to disable the double precision and enable the TF32. Okay, if you want to run this way. What happens here? We run the same way, but we get approximately 6 times faster performance that we used to get for double precision. And this is because simply there are more Tensor cores than normal cores on the GPU that would run the double precision computations. Okay, so then we also measure the compute flops on the CPU. We do again a matrix multiplication, but for the CPU now, running also the same way, and we get some decent performance on the 4 CPU sockets. Something that I'd like to note is that the benchmarking, like running our code, revealed, let's say, a bug of OpenBLAS, because it uses 1 extra thread, maybe not a bug or quirk. So that's why if you noticed, we use 71 OpenMP number of threads instead of 72 MP number of threads, because if you do 72 here, then your performance will degrade. So this is actually a good use of our tool, because not only we test our system and performance, but also we can see, for example, one scenario would be if you want to evaluate the NVIDIA performance libraries for your application. You would use this benchmark and you could link it against this library and test the performance there. Okay, what else? So now we pass on the measuring the memory bandwidth. So this is a benchmark that does a stream benchmark, again from our tool here. We're interested to answer the question, how many threads do we need to achieve maximum bandwidth? So with 1 thread, then we get to the 14 gigabytes per second, which is pretty low for what the CPU, Cray CPU offers. Then we get to really close to hardware limit of 500 gigabytes per second using 64 number of threads. There is actually a case that I wanted to show. So when we doing the network bandwidth between CPUs on the same node, and we use the OSU benchmark, when we run on one node, we use 2 MPI rings, 64 number of threads that we saw that we can get actually the maximum performance. And what we notice here is that up to 512 kilobytes of message size, the performance is actually decent, because this goes, remember, this goes through the Grace interconnect, which is 75 gigabytes per second. While when the performance, when the message size goes 1 megabytes or larger, the performance starts to drop. And it gets actually and saturates kind of there with 14 gigabyte per second, which, if you remember, it's the first result here when we ran the streaming benchmark with one node. So what's happening here? First of all, the protocol switches from the, let's say, the cache-friendly eager PI protocol to rendezvous, and then because it's not cache-friendly anymore, and there is a lot more synchronization kind of happening when you have this protocol and also a larger message size. The MPI, since you are on the same node, it switches to shared memory copy, actually. So single thread is shared memory copy. Why single threaded? Because normally when you start to do an MPI init, it will by default go to single threaded. And then this copy, actually now, this messages happens with one single thread, and that's why it matches the 40 gigabyte per second that we saw with single thread for the streaming benchmark. Okay, so 2 more slides. We also measured network bandwidth between GPUs on the same node. We run in this way, right? I've put the Affinity script here just to show that way to use it. And yeah, it achieves like 120 gigabytes with the message size of 4 megabytes, which is basically the NVLink limit, theoretical limit that we saw on the first slide, because it's like, and within the same node, it goes through NVLink GPU to GPU, and that's what you get. And we also tested on different nodes, and this actually is not within the node anymore. So we have, it goes through the network, and we saw that the network bandwidth was around 25 gigabytes per second, and really get very close to that bandwidth. So yeah, with this, I'd like to give the floor to JG. This is my part, so I'd like to also maybe wrap up my part. I want to close with a message that I want to say that make sure to use all 4 GPUs on the node and check the performance of your environment and of your code, because GH200 nodes are not configured for the job to fail, but allows to run with degrading performance. And now, I don't know what, should I stop sharing and leave it to JG to continue?
Hello, can you hear me?
Yes, we can hear you.
Okay, so just a reminder, thanks Andreas and Daniel. So just a reminder about this page where you can ask questions. I see that people already started, so it's good. So in my part, I'm going to talk about performance and debugging tools. So maybe I will start with a comment. This is going to be an introduction, just not a training about how to optimize your code. I just want to show you a few tools that we like to use at CSCS. I can't see the questions that you're asking, so I won't be able to answer before the end of the talk. But my colleague will. I'm going to focus on HPC use case because we don't have time. So I'm not going to talk about containers or Python applications, but in general, you can apply the same techniques to this kind of workflow. So I'm going to talk basically about three tools, NVIDIA tools, Linaro tools, and Scorpi and Scalasca if I have time. So I'm not a tool developer. So if I say something wrong, it will be because of me, not because of the tools. And I think it's nice to have choice because sometimes you want to have choice. So I guess it's okay. I hope it's okay for you. And I guess that you are here because basically you need a debugger, a debugging or a performance analysis tool. So why do you need a debugger? Well, sometimes your application just doesn't run or just crash. It runs and then it stops running and you don't really understand why. So that's what a debugger can do for you, can tell you why. And the performance analysis tool, well, it can explain why your application is running slow or not as fast as you would like. Okay. So typically, when you do debugging or when you do performance analysis, it's a repetition of different tasks. First, you have to use the tool on your application, then you look at what the tool is telling you, and then you change your code and you restart again. So let's start with the NVIDIA tools. Yeah. So NVIDIA Nsight, it's a set of tools for debugging and profiling your application on NVIDIA GPUs. And inside Nsight, you have two tools. The first one is Nsight System, which is a high-level performance analysis tool where you can identify where your application is slow. And then you have Nsight Compute, which is a more advanced performance analysis tool, and it's designed to explain why your CUDA kernels are running slow or how you could change your code to run faster. So Nsight is available at CSCS with basically any user environment that comes with CUDA. And so, for example, here, if you pull and start the program GNU, you will pull CUDA and the compilers, but also the tools, so NSYS and NCU. The nice thing about Nsight is that you don't really need to recompile your code. You just need to submit your job with NSYS profile as before on Alps. So if we look at the list of arguments, you can trace different parts. You can trace CUDA, you can trace cuBLAS, you can trace MPI, and even more. It's possible, if that doesn't work, then there is maybe a problem on CSCS side, but that should work. You can also do memory profiling, and when your job ends, and if your job doesn't, is a success, the tool is going to create one or more NSYS file. And if you install the client on your laptop, you can open that file, which you have to copy before opening. You will see this kind of user interface. And here it's just a screenshot of one application. It's not important. Don't look too much at the numbers. It's just an example. What's important is to see that the tool can already tell you how much time you spend copying data between the CPU and the GPU. So from host to device in green, and from device to back to the CPU in red. And then in the middle, you have the kernel calls. So of course, on the Grasshopper, with the unified memory, you should not see that too much, but it still helps to detect performance bottlenecks. So for people who don't really like using graphical interface, you can use NSYS stats to extract data directly from the report that you created with NSYS profile. So Daniel was showing the performance of node burn with double and reduced precision, and he was saying that you can go from one, you get 6 times faster by using reduced precision, and the tool will show that actually, yeah, it's because it's using an optimized cuBLAS gem function. So that's already confirmation why the code is running faster. And you can get more details with the help flag. Okay, so back to the user interface. Now we are moving to Nsight compute. So same thing, you just add LCU to your job script. But you have to be careful that because the tool needs to collect the performance data, the tool needs to replay the kernels multiple times, and that's going to add maybe sometimes a lot of overhead to your runtime. So one way to focus on what you want is to use NSYS to find which kernel is taking most of the time, and then to run NCU with the kernel name flag, and to focus, and then to collect data only for that kernel. And then you can also add more flags to be more flexible. So similarly, the job will create one or more NCU report files, and then you can open them with the client. The nice thing with NCU is that you don't have to copy the file to your laptop. You just need to, you can open it remotely from the menu. Okay. And then here, that's the first thing you can, by default, NCU will collect what they call the speed of light performance data. So it's general overview of the performance of your kernel. So you have to be careful that here you have a menu where you can choose the invocation of the kernel call. And in that case, because we are using node burn, of course, the GPU utilization is very high. The memory is also relatively high. Well, yeah, it's a GPU burn, so no surprise here. So again, if you don't want to use the graphical interface, it's possible. You just export the data with the CSV flag, and then you just plot the data the way you want. So that's what I did. By default, so NCU will use the speed of light list of performance metrics. And actually, if you look into the installation dir of NCU, you will see that there are some section files, and you will see the list of performance metrics that the tool is using. If you want to do advanced analysis, you can tell NCU which section or even which performance metric to record, and then you can focus on what you think is more important. And so if you run NCU with the section flag, that's what you will get. You will get something a little bit different from before with more performance metric. And then it's get interesting to understand what the tool is trying to tell you. Okay. So that's all for NVIDIA. Now I will jump to Linaro. So I guess everything is fine. I can't hear anyone anyway, so I guess it's fine. So Linaro is another provider with providing debugging and performance tools. So today we have with us Rudy from Linaro with online, who can answer questions if you have any. And basically, I just copied what he presented in March at this in this PDF. So Linaro has a debugger. So yeah, it's called DDT. It's a parallel debugger, and it works with basically everything that you can think of. And then you have MAP, which is the performance analysis tool. And actually, performance report is a light version of MAP in case you want to have a very quick way to get an overview of the performance of your application. So Linaro is doing a good job at supporting a lot of different platforms. So it supports Intel, AMD, and NVIDIA GPUs, and a bunch of other stuff. So the tricky part is that if you want to use Linaro at CSCS, you have to load 2 user environments. And the motivation here is that we don't want to add the tool in every possible user environment that we deliver to the users. So basically, you just pull the compilers, you pull the tool, and then you mount them. So on the /user environment and the /user tools directory. The thing you should do is that you load only one view, because you want to keep using the compiler from the first user environment, and because we have also compilers in the tools user environment, you don't want to overwrite. I mean, you could if you want to, but then you will need only one user environment. I hope I am clear here. But basically, that's how you should do things, and then you will see that the tool is there in your path. Okay, so now that you have the tool ready, the first thing that you need to do is to install the client on your laptop. And we try to write some documentation about that. So I will just point you to the documentation. And then when you want to start a debugging session, you click on the remote launch menu here that will connect you to Alps. So in that case, to Daint. And then you can click on the manual launch menu here. And then you specify the number of processes that you want to debug. Is it a CUDA code or not? And then the debugger will tell you that he's waiting for you to connect on Alps. So you go to Alps, you recompile your code with debugging flags for the CPU and the GPU, and then you add the DDT to your job script. And what will happen is that on your laptop, the client will, by default, will stop on the first call to MPI init. And that's what you will see. So that's the user interface of DDT. So you can see you have navigation controls where you can pause the execution of your executable. You can also step into, step over, step out of function calls if you want to go down the call tree. Then you have process control where you can navigate between processes. Processes can be MPI ranks, OpenMP threads, or even CUDA threads. You have the files explorer if you want to navigate into your source code. And the most important view, I guess, is the source code view, and DDT will show you where the execution is happening. You have the variable explorer, so where you can inspect your data. You can also compare the values between processes. You have the call stack view, so that's where DDT will tell you where your processes are, and the evaluate view if you want to monitor the value of some variables during the execution. So that's very nice. So as I said, the debugger will stop on the MPI init, but you have two scenarios. The first scenario is, okay, you have an executable that crash at the end during your job. And so in that case, you just start your application and then wait for it to crash and stop, and the debugger will tell you where the problem is. If your application doesn't crash, but you think there is an issue somewhere, then it's up to you to ask the debugger to pause the execution. And to do that, you just add a breakpoint. So you go to the source code view and click on the line, and then you will see a little red dot. And basically, you're telling DDT to pause execution. And then you click on the green arrow here, and then it will resume. And then DDT will automatically pause the execution when it is reaching a breakpoint. And then you can see where things are. So basically here, in that case, I can see that I paused in the compute energy function, which is what I wanted, and then I can inspect the values on that line. Of course, you can do the same with GPU. So I will go fast, but basically, if you know that there is a problem in the CUDA kernel, you just put a breakpoint there, and then DDT will pause inside the GPU, and you can use the stack view to look at the number and the location of the CUDA threads. And there is also a nice way to navigate between CUDA kernels is the kernel progress view, where you see the state of the GPU. Okay. So yeah, maybe one more thing. If you don't really know where or what CUDA kernel is being called, you can ask DDT to stop in every time that CUDA kernel is being called or launched by going into the control default breakpoints menu, and then it will stop every time. That could be that's possible. Here, so I'm just showing an example of how to navigate between CUDA threads. So you can use the navigation control or the kernel progress view, and then you can compare the values between blocks. Okay, what time is it? Okay. So you can inspect variables, but you can also inspect arrays and distributed arrays by opening the MDA viewer. So basically, you can view data in a table form or even in a nice, let's say, yeah, chart. It's possible to export the data in text or binary format, HDF5. You can have statistics about your data. You can filter data if you want to focus on some values. You can also do memory debugging on the GPU. So basically, you just have to click to enable the memory debugging when you launch the client, and then pause the execution and select memory usage from the menu. And that's what you will see. So you will have a menu for every GPU, and you will see the memory usage on every GPU. You can find out how much memory is allocated. You can track between the for every allocation, you can go back to what part of the code did the allocation. So it's a nice way to see where your code is allocating a lot of memory, or even find memory leaks. Okay, so that's the end for DDT. Just a few things. It's a licensed product, so CSCS is limited to 128 processes. It's a shared license, so if we have too many users, then you will have to be patient. If you really want more, then please get in touch with us. We can discuss. We currently have a license only for NVIDIA GPUs, not for AMD GPUs, but Lumi, it's possible to use the same tool at Lumi. Okay. So Linaro is also doing performance analysis tools. So same as before, you use the same, you load the same user environment. In that case, you want to keep the optimization flag because you want to do performance analysis, and you want to add the line and info CUDA flag to help the tool showing performance data. And then you submit your job this way. You just basically replace srun with map. And by default, you will get useful information. But if you want advanced data, then you can add the CUDA kernel analysis flag or the CUDA transfer analysis flag to map. Okay, so the first thing, when well, after your job, map is going to generate a map file. And the first thing that you can do is to use perf report, which is the light version of map, and it is going to generate HTML or a text report by default. You can also generate a CSV report if you want to export data, or you can even just ask map to write the report at the end of the job directly. So high-level overview, you can see the most time-consuming region in your code. It will also show a nice radar chart. And I guess the most important thing is that it can give you a list of useful advice. You will get more details in the documentation. Okay, so yeah, so if you go into the perf report, you will see that it gives you information about how much time you spend doing computation, how much time doing communication, I/O if you're doing I/O, and OpenMP, which is also computation, but it's sometimes nice to know what's happening on the OpenMP side. So, and then if you want, you can also use the data to make your own chart, which I did here. Okay. And then the second part of perf report will give you information about memory. So it's unified memory, so it's not very useful here. Of course, accelerators, energy, it doesn't really work on Alps, and Fred Affinity. I mean, yeah. So energy map will collect only energy data from the GPUs, but on Alps it's possible to get more. And I will recommend you to use the energy counters directly from the file system here. And then it's not very hard to read that kind of energy data, and you will get compute node, CPU, and GPU level energy data. And then if you read the counters at the beginning and at the end of your job, you will get the energy of your job just in Joule. The sampling rate is 10 times every second. And again, you can do nice plots like this if you want to. You will get node level energy data just by using the saccount command, which is reading exactly the same, which is getting the energy data from the same files. Yeah. Okay. Okay, so what should we do? Should I finish this and then stop?
You can go 5 minutes more, but not more than this, I would say.
Okay. Okay, that's a shame because I wanted to talk about Scorpy, but let's do that. So then if you move to map, you will get more advanced analysis. I will go quick. Yeah, I will go super quick. Yeah. So yeah, it's possible to run map and to get a nice view of the timeline of your application, of the performance of your application over time. And by default, here, for example, you can go to the GPU kernels tab and it will tell you which kernel is using most of the time. And then you can zoom in on the region of interest if you're interested. I'm sorry, there is more details in the PDF, and if you have questions, we can talk after the talk. You can do the same with memory transfer between the host and the device, and you can also export the data if you want to. Okay, I will take 2 minutes to talk about Scorpy and Scalasca because yeah, I think it's important. So Scorpy and Scalasca are tools that are developed by the Virtual Institute for High Productivity Supercomputing. It's an open source tool, so you don't need a license to use it. And Scorpy is one of the tools that they support. So there are 2 ways to use the tool. You can do profiling, and let's just give you an overview of the performance of your application. But if you really want to understand why your code is slow or not doing what you want, you have to do tracing because it will be much more detailed. Okay, so again, you just pull and you load the user environment on Alps, and then you will have the tools. In that case, there is a trick. If you need to compile your code with CMake, it's a 2-step process. You just deactivate the Scorpy, do your normal configuration step, and then you activate Scorpy and build your executable. So you need to rebuild your code. And then you just choose profiling or tracing. And by default, profiling will create a performance file in a performance report in the cube format, and the tracing will create a report in the OTF format. Okay, so yeah, profiling, basically you run your job as usual, and then you have to transfer the report file to your laptop and open it with the cube client. And then you will see that, oops, the report is divided in 3 parts. So you have the performance metric part on the left, where you can choose the type of metric you want to look at. You have the call path or the source code view in the middle, and then you have the system resource view on the right, where you can understand the difference between the nodes or GPUs or this kind of stuff. And everything is colored by importance. Okay, same thing with tracing. You have to use you have to activate tracing. Usually there is also an overhead associated with the fact of tracing. So your job will run longer, and so there's a way to reduce the overhead by using a filtering file. I don't have time to explain, but it's relatively easy to do. And then you use Vampir you run your job, and then you use Vampir to view the performance report. Okay, I think I will stop here. Yeah, so the nice thing of Scorpy is that it's also available on AMD GPUs. So it's available on NUMA. Yeah.
Thank you so much, Jean-Guillaume and Danielle. I think I'll give you an opportunity for raising hands if you want to ask a live question right now. I don't see any raised hands, so you can keep asking on the Q&A document. thanks all the speakers and thanks everyone. Oh, we have one question. Please, Benedict, you can unmute.
Yes. I have a question regarding debugging with C++ and templates. Could you comment on this, please?
Yeah, I don't know if Rudy is online.
Hi, yeah, I can answer some of that. So templated code is, it should work with the debugger, so you should be able to see some of the variables that goes into it, but the support isn't complete for some of the more advanced C++ template features. So at the moment, our developers are working on improving that, but at the moment, and some of it will work, but some of it won't come up in the UI. And kind of is the question around this more around sort of the COCOS model and debugging sort of COCOS code?
It's a bit low, so maybe we can do it in the document as well to make sure that it is readable. So thanks. Any other question? Please raise your hand. Otherwise, we are closing the session. I don't see any. So thanks, everyone. Wish you a good rest of the day and see you next time. Bye.